Okay, welcome everyone to After Hours for CSEUFLEX. So the plan for today, at least, is to go over linked list and queues and stacks for the most part. And before we get to that, I want to kind of provide like a brief overview of what it means, what big O means, and then I'll speak a little bit about arrays and dynamic arrays. All right, so just a second, I'm going to share my screen now.
And if you want to ask any questions, just unmute yourself or use the Slack channel on the After Hours channel. Okay.
Yeah, you can just unmute yourself if you don't want to have to type a question. So the thing about the big O thing is that you're going to be covering it in detail next week under algorithms. But just because some of what Melky and Ifyo could speak about later today, some of it will be centered around big O. So it's kind of a prerequisite. That's why I'll just give you like a brief summary of what it means and why we talk about it. All right, and luckily the training kit is kind of it's kind of a good information source. It's quite in depth, so that's why I'm just using it to kind of explain a little bit. All right, so Big O, the whole point of Big O is measuring the speed of your algorithm. So you have an algorithm, you want to know how fast it is, and that's where Big O comes into play, right? So let's assume, let me just find, okay, sorry, I'll just make this Python. Okay, let's assume we have some random function func that takes in some inputs and does something with it. It does something, right? I want to know how fast this algorithm is. I mean, one possible way of doing it is you measure the time this algorithm starts. So you do something like start time, dot time. Then when you're done, then you do end time, dot time. Then total time equals end time minus start. So this is one possible way. We check the time when you start running the algorithm, and then you check the time when you finish, and then you subtract, then you get the time that this algorithm runs for. But what if my computer is really fast? So it means this would happen really quickly, and I would have a small time. But then I go to a different computer that is kind of slow, and then it varies. So on my computer it takes, let's say, a second. On a different computer it takes a minute. So of course that's not a very good measurement approach because it varies too wildly and it's not consistent, and it kind of depends solely on the processing power of the computer. So that's why we can't use the actual time that your algorithm runs for. So that's where BIGO comes into play. So what BIGO does, right, is it measures how fast the speed of the algorithm changes as the input changes. So it's more of a ratio of how much your algorithm speed changes with respect to the input size, right? So let me give another example. So now let's go back to this our example. So now let's assume inputs is a list that contains just one item, and then what this does. Okay, let's just make this a list. So it's just an array. And this is for, let's say, total equals 0 for number in R, total plus equals number and total. I'm trying to sum. So what this algorithm does is that it sums up whatever array is passed in. right? So total is 0 initially. Then we loop through each number in the array, and then we add the number to total, and then we return total at the end. So that's quite simple. Now let's imagine we call this with an array that has just one element, 1. So you expect this to be very fast, right? Since it just goes for 1 in this array, it adds 1 to total and it returns 1, and that's it. But then what if this has a million items? This goes from 1, 2, 3, 4, up to a million. That's it. So of course, this is going to take a lot more time because it adds 1 to 2 to 3 to 4 to 5, and it keeps going. So I mean, this algorithm grows. The time the algorithm takes grows as the input changes. So when you have one item, it takes a small time. When you have 8,000 items, it takes a slightly larger time. When you have 1 million items, it takes a really large time. And when you have a billion items, it takes more time. So it means as you add more inputs, your time increases. So we call that in big O terms, we call that a linear runtime because your time varies linearly with the inputs. So, and that's what it's written as big O of n, because let's assume n is the length of the inputs. In this case, n is the length of the array. So your algorithm varies as n increases. So we call that big O of n. But then that's one case. But then in different case, let's assume this algorithm, the only thing it does is that it adds, the only thing it does is that it adds the first item to the second item. That's what it does. So if we call this algorithm just 1 and 2, it would add 1 and 2 and return 3. But then if this array had 1 million items, so it goes from 1, 2, 3, 4 up to a million, what would this algorithm do? What it does is it adds 1 to 2 and returns 3. So it means no matter how this changes, your runtime doesn't change because it's doing the same thing over and over. So what we call this is big O of 1 because it's constant. You just use 1 as a constant value. So this is a constant time algorithm because no matter how much your input changes, it does the same amount of work each time. So this is kind of the sweet spot of big O because this is kind of the best you can get. So let me just show you the available ones, what we have. So like I said, we have constant runtime, which is this example that you have here. So it means no matter how the input changes, you're doing the same amount of work, which in this case, you're assigning 5 to X. So it doesn't change. And that's kind of what you used before. If you get a constant time runtime, then you're really good. Like you don't go on that problem. So that's one. The next one I said is the linear runtime, big O of n, which means what you're doing varies as your input size increases. Because in this case, we are printing all the values in the array. So if you have 5 elements in the array, you're printing 5 times. If you have 10 elements in the array, you're printing 10 times. So it means the amount of work you do varies as the input increases. So that's linear, which is good. It's okay. It's acceptable. So now there's also logarithmic. That's big O of log n. What's can you guys see my screen? Okay.
Yes.
All right. So there's also
we can see.
logarithmic. Okay. Thank you. There's also logarithmic. What logarithmic means is that each time it runs, it cuts what is left by half. So let's say you have 100 items to process. When you run this the first time, it becomes 50. When you run the second time, it becomes 25. The third time, it becomes 12.5. So each time you run it, you have the rest. So no linear, when you run the first time, you have 99. Second time, you have 98. Third time, you have 97. Or with logarithmic, you half it. So 100, 50, 25. So you can see that's a lot faster than linear. And it's also really good. If you have a logarithmic runtime, it's a good solution. So in this example, you can see it takes an input. We get the length of the inputs as I. So as long as I is more than 0, we print I, then we divide I by 2. So whenever you're seeing something that has to do with halving the input size at iteration, then it's logarithmic. And that's also really good. So then we have n log n. N log n is like a mix. It's kind of a mix because, I mean, it's not compared to big O of n and log n and 1, it's not very fast. But really, when you get to sorting algorithms, you see that with sorting, the best, when you're sorting things that are not, that you're not sure of the order, the kind of best runtime you can get is n log n. You can't really get anything better than that for the average case anyway. But then these three, they are not really good. So this is Aries power something, series power n, and n factorial. They're quite bad, and you kind of, if you come up with this kind of algorithm, then you should probably think of ways to improve it, because they're not really fast. So yeah, that's kind of big in a nutshell. So we have this graph here that shows the different runtimes and how so n represents set of data and capital N represents number of operations. So let me just zoom in a little bit. So the purple line is constant runtime. So you see when we have 0, when n is 0, it does the same thing. When n is 100, it does the same thing, the exact same number of operations, and that's good. Now for logarithmic, that's log n, logarithmic runtime. So it varies slightly, just slowly. It's like just a very slow increase, which is also good. Then you have square root of n, which is also good. Then you have n, which is linear. So as you increase it, it increases linearly. Then this is n log n. I mean, it's not very good. It's not good, but it's okay. It's not too bad. But then these three, they're quite bad. When you have n squared, 3 power n, and n factorial, and it's like almost a straight line. So if you increase the inputs just by very tiny amounts, it goes up rapidly. So yeah, it's not very good. So there are a few examples here. Like I said, in this case, constant time, it just prints the first item in this array. So of course that's constant. Linear time, it prints every element. N square, so it loops twice. So for each element, it goes through the entire array. So it means by the time you go through the entire array, you've gone twice. So a good way to identify quadratic runtime is when you have nested for loops. So when you have nested for loops and the work in this for loop is being done for each element, then you know it's n square. So you see the clue is nested for loops. All right, I think that's kind of a very good overview that I don't want to go too in depth because you'll still kind of go over this next week in class. So that's kind of a brief.
Victor, I have one question just about how you actually test where it ends up on that scale. Like, is there, like, how do you find out if it's logarithmic n or squared or whatever?
So you would go over this next week, but just to give you like a brief turn, right?
Right.
So things like print. When you see print, it's constant. Like this is constant. Because like statements are constant time. Loops are linear time. So just keep that in mind. Statements are constant time. Loops are linear time. So print in this instance is constant time. So this is big of 1, and it happens only once. So so it just prints once and that's it. So that's constant time. So now let's go for this. When you see a loop, it's linear time. So for this line, let me just kind of write something here. Hold on. Let me just start from here.
Victor, you just said like when you see a loop, sometimes there's a loop, but it has like different conditions. So I don't think that's accurate. Like you're saying, when there's a loop, you think it's linear time. Sometimes in the loop, we can have a specific range that doesn't constitute the linear time. That's what I'm just trying to say.
Exactly. I'll kind of go into that just in a minute. But thank you for that comment. All right. So now let's start from constant time here. This print here is constant. It's printing just one item, and that's it. So it's constant. So this is big O. It's kind of hard to write with a mouse. Well, anyway, with the trackpad. So this is big of 1, and that's it. So it means the entire algorithm is big of 1. Now let's go to this next one. So we have 4 items in items. So it means this goes through every item in items. It goes from the first to the last. So whenever you say this, so this line, just this line alone, is big of n. Since it goes through the entire array. Remember, let's assume this went through if this went through in range 2, for instance, just the first 2 items, then that's constant, because it doesn't matter how big n gets or how big items get, it only does those first 2. But in this case, it goes through the entire items array. So this line is a big O of n. And then we go to the next one. That's the nested, that's print item. And like I said, print is a constant time. So we have this line is a constant time. So it means we have constant time in big O of n. So whenever we have things in something, we multiply. So we do big O of n times big O of 1, and that's big O of n. So this entire algorithm is big O of n. Now let's go to the next one. Okay, now let's go to the next one. So we have items as the inputs. Our first for loop goes for item 1 in items. So it goes through every element in items. So what does that say? It says it's a big O of n. So that line alone is big O of n. Then go to the next line. For item 2 in items, once again, it goes through every element in items. So that's also a big O of n. So that line. Yeah, and just like you said, it's only a big O of n if it goes through every element in the array. If for some reason it stops at an element or 2 elements before the end, then it's constant time. So it's only linear time if it goes through every single element in that array. So only if that's it. So now the final line is printing. So printing is big O of 1. Big O of 1. And now when things are nested, we multiply. So big O of n times big O of n is big O of n squared times big O of 1. Big O of 1 doesn't matter in that case. So we just pick big O of n squared. And that's what we have here. Yeah, so do you guys understand? Do you have any questions about that so far?
No, that's good. Thank you.
Yeah, so like I said, you kind of go into more detail with this next week. So I don't want to spend too much time on this for now. So yeah, I think that's where I'll stop on this for big O of n. All right, so the next thing I want to talk about is dynamic arrays. So we know regular arrays just mean like a contiguous block of memory that stores data. So let's assume you have a block of memory. One array is that you have a continuous block that stores data. That's what an array is. So regular arrays, when you are creating regular arrays, you specify that this array is going to be 5 items big, and it looks for a space in memory that can hold 5 items, and it creates that, and it gives it to you that's your space for the 5 elements array, and that's it. But then what if you want to add a 6th item? You're not able to, because it's full already. That's where dynamic arrays come into play. And remember, dynamic arrays are what you have when you use lists in Python. They're called dynamic arrays. They're dynamic arrays, but they're called lists in Python. So what they do is that once the array gets full, it increases itself. So you create an array at first that has 5 items. Then you want to add a 6th item. Then what happens is that it looks for a space that can hold 10 items. So it doubles 5. It looks for a space in memory that can hold 10 items, and then it copies everything one by one from the old array to the new array. So it means in your new array, you now have 5 extra slots to store more data. So copies everything over from the old one to the new one. So that's all dynamic array means. So it means as you add more data, your array grows, and as you pop more data, your array shrinks. So just like a really smart way. Of course, there are lots of details that I'm skipping because they don't really matter. But that's like the core functionality. As you add more data, your array grows, and as you remove more data, your array shrinks. So it does this, of course, efficiently and in the most performant way possible. But that's kind of like the core gist of dynamic arrays. So, so any questions about what I've said so far, or anything clear on?
So if we have, sorry, so to understand it, if we have five spots in the dynamic array, and we want to add a 6th one, the dynamic array create one more spot for the sixth one.
Well, it doesn't. That's kind of the idea. Well, it can't keep creating one, because what if you want to add another one and it creates one more, and that's kind of slow. So what it does is you have 5 that is already full. You want to add a sixth one. So what it does is that it doubles that. So it looks for a space that can hold 10. So 5 times 2 is 10. Then once it finds a space that can hold 10, then it copies all the elements from the old one to the new one. It copies the 5 elements and it adds the sixth one. So you now have 4 extra spaces that were used. So you can keep adding. And once you reach the end of that one, and it finds a space that can hold double. So 10 times 2 is 20. So it looks for something that can hold 20 elements, and then it copies it over, and then it keeps adding. And then once that's fully doubles it. So it makes it so effectively on the average, it doesn't add. That's why on the average we call appending to an array a constant time operation, because even though sometimes it doubles and that's big of n, it doesn't happen often enough to warrant us to um to reduce our runtime. So that's why we just kind of stick with big of 1, because that's kind of the average. On the average, it wouldn't copy anything over, and it wouldn't double anything. Is that clear?
Thank you, Victor. Thank you.
Yeah. So yeah, I think that's it from me. So if you want to take over.
Yeah, that's fine. Okay, let me just share my screen. Okay, can you see my screen?
Yes, we can.
Okay, all right. So we'll just do a quick rundown on linked lists, talk about singly and then the doubly linked list. Then if I'm still within my time limit, or perhaps solve a simple problem to sort of get a better grasp of it. So I know Tom already explained to us what linked lists are and what they have in them. So we're just going to Google out a definition for linked list. So basically, a linked list, according to Geeks for Geeks, is a linear data structure, yeah, where the elements are not stored at contiguous memory locations. Then the elements in the linked list are used using pointers as shown to the below. So let me just give a more basic the explanation of what linked lists are. So Victor just talked about dynamic arrays, yeah? So just look at the linked list as arrays that, now, you know, in your regular array, say you have something in the lines of, say 1, 3, 4, 5, whatever, yeah? In your regular array, you can easily, let's say this is an array called A, right? So you can easily, if you wanted to get the first element in that array, would simply do the basic stuff of A or 0, and then we'll get 1. In order to get the last element, and that's something like A of say 3, and you'd get 5. Yeah. So for our regular arrays, we can put in the index and get them, but when we talk about linked lists, it's kind of different. The way they're set up is different, but linked lists sort of are dynamic arrays because you don't have a fixed, how will I put it now? You don't have a fixed size for a linked list and say the length is so and so. You have to keep moving. So now we have singly linked list, and then we have the doubly linked list. Now for the singly linked list, we have the head, which is the first element. The head is going to always be the first element. Then we have the next node. So we have, let me explain the terms basically. So we have the head, which is the first element. We have the tail, which is the last element. We have pointers, which sort of point us to the next element. And then we have the node. And I'm going to, just a second, I'm going to show you a diagram that sort of gives a very good explanation of all these terms. And then we have the next element, which is sort of like the next element. So in this case, if you want to figure out these terms in this list, we'll have something along the lines of this. Let me do this. So that we have visuals to sort of see. Okay, so if we're looking at this linked list now, okay, so we have 1 as our head, we have 5 as our tail, so we have the pointers, okay, and then we now have the nodes. Now the nodes, I will show you in a bit, sort of like the value. The node carries the value and then the link, okay? Then we have the next. So in this case, this is an element. This is our current element. So the next element to 1 is 2, and the next to 3 is 5, and so on and so forth. So now for singly linked list, we can only go forward. So there's no reference to the element before the current element. So we don't have the previous. So that's why we have the doubly linked list. So the doubly linked list basically has everything a single list has, plus an extra helps point us to the previous element. So this helps us to, if we want to go back or want to go forth. So in this case, this would be this is how our doubly linked list would be. So we can go to the next element or we can move to the previous element. Okay. So now I opened up a diagram that sort of gives a very good explanation for this. So now this diagram shows our linked list. So this is our head element. So see the explanation of a node here. It carries the element itself, the content of the element, and then the link itself. So that's the node. So the node carries the content and then the link. So we have, in this case, we have 3 nodes. Then we have the element itself. It points to the next one, and then it points and it keeps on going. So in this case, this is our tail, and then this is our head. Okay. And looking at this, obviously, this is a singly linked list. It goes in one direction. I have another diagram that sort of shows a doubly linked list. So in this case, it goes in both directions. So because this is our head, so the head doesn't have a previous, so that's why it's null here. And then we keep moving. We have the next previous for each of the elements. And at every point in time, the element that we are currently working on is our current element. And then the tail doesn't have a next, because that's the last element, so like there's no next there. Okay, so like that's a very rough and quick explanation of like the basic concepts behind a linked list and how linked lists are structured. So before I move forward, does anyone have any questions or any concern? Okay, I'm going to take silence.
Sorry, I do. I'm just wondering, in an array, like when you're specifying the elements, you can clearly read it. Like you can see on line 10, you have there like a tree, or if you're referencing an element in an array, you can do that.
Yes.
With linked lists, like how do you specify what node you want? Or like, I feel like you can't, like, it's just like this invisible thing going through methods on a class, but we can never really see like the node where we're at. Or I don't know if I'm explaining that very well.
Okay, so I'm just going to show a little of it, and then we're going to solve a problem that will use a concept of moving so that it sort of gets better. But
yeah, thanks.
say we wanted to, looking at this linked list, we wanted to get, say, what the value of the second element is. We would have our head. Okay, that's it. So we have the head. Know that our head is let's set our head. So I'm trying not to confuse you now, but let me, as it is now, looking at line 6, okay, we have our head as 1. If you want to know the next element to our head, the next node will be head.next. That points to the next one, okay? And if you know what the is, at that point, it will be head.next value. Okay. So at this point, this is how we get these two. So it might look kind of complex and like, why are we passing through all this when we could just, do this with the regular arrays? But linked lists sort of have lots of advantages when you are working with data structures and other algorithms, which as you move along the line in CS, you're going to see the importance of understand it. Okay. So I'm going to solve a rather straightforward linked list problem, and then hopefully that's the understanding. Okay. So the problem we're going to solve is sort of, let's see, four, five, 2 again. Okay. And let's see, 3. Okay. So the idea is you're given a linked list and you're told to get rid of the duplicates. So looking at this, we obviously know, like by sight, that we have duplicates of 2 in this linked list. So we're going to try to use the linked list to solve the problem, but let's try to look at it and try to solve it without, writing code first. So looking at this, let me write it in my linked list format. It looks have this. Okay. All right. So looking at this, what we'll do would be to look through this linked list, and then we're going to point. Next time we look through the list, we're going to be saving. We'll do the best way to do this, like the fastest way to do this really would be look through this and just save values inside, say, an array or something. Okay. Now looking at this here, we have our head as 2, and this don't confuse anyone I'm talking about. Okay. So this is going to be our new value. Let me call it our new linked list. And then let's call this our tracker. Okay. So what we're going to do is when we are on a node, we're going to put it in our tracker. Okay. And if we put a node on the tracker, we're going to answer a new linked list. Now, at the point where we reach an element that is already in our tracker, I'll delete it, and then we're going to do a little bit of manipulation. Okay. So now our first element, our head element is 2, right? So there's nothing in our tracker. So we have 2, and then we add 2 inside our new linked list. Okay. Now that's easy. Now the next one, our current elements dot next is 4. Okay. So now we check our tracker. There is no 4 in our tracker, right? So we set 4 in our tracker and we add 4 to our new linked list. Okay. So now the next one, we're currently on 5. Now we check our tracker. We don't have 5. So we add 5 to our tracker and we add 5 to our linked list, basic stuff. So now at this point, which we are here, we're on 2, we check our tracker and we have 2 already in our tracker. So we have to get rid of 2. So now our current element is, we're currently on 5, and current.next at this point, current.next at this point is 2. Okay. So in order to skip this guy, delete this guy, and get rid of the duplicates basically, yeah. So our current.next will be this value. So current.next is 2, current.next is 3, right? We check our tracker, we don't have a 3. So if we add our 3 here and we add our 2 here now, sorry, we add our 3 here, sorry, and now we don't have any duplicates. So now what happens is you delete the pointer. So for linked list, if you think about it, it's not like it's really deleted. You just remove the pointer and point it elsewhere. So it's sort of like saying, looking at this and everybody's pointing at something. And at this point, 5 sees that 2 already exists and decides to, point at 3. So it sort of deletes the whole of this and then we're left with our linked list like that. Now, if this explanation of what we're going to be doing confused you in any way, just relax and let us actually solve the problem, okay? So what we'll first do, let's take in a doubly linked list. So we'll just assume that we have a doubly linked list in here and call it, let's just call it doubly linked list. Okay. All right. So now the function we're going to be building, let's just call it remove. Remove prefix. The function is going to take in our doubly linked list. Okay. So now I'm just going to write down sort of like pseudocode on what we want to be doing. So I'm just pass that. Okay. So now the first thing we're going to do is to check the linked list, and we're going to check if the linked list is empty, and if it is empty, then we return none. So now if we have an empty linked list, then we don't need to bother about doing anything. We just return none. Okay. So let's have check if linked list is empty and return none if empty. Okay. Now the next thing we'll do after that is to set our current. So we're going to start moving through each node element basically. So we'll set our current. So let's write in English. Set current node to the head. So the current node value to the head. Okay. So from there we'll just keep moving. Now, okay. So now the next thing we'll do is our tracker. So let's set a tracker that holds the current element and in array. Okay. So that's our tracker. We'll set our tracker so that each time we move through, we're going to be saving it basically in there. All right. So after we set our tracker, the next thing we're going to do now is to actually like write our loop. So write a while loop for while our current element dot next is not known. So basically, we're as far as we're not on the last element, we want to keep on moving, right? So while our current the next element is not known, what we're going to do now, first we'll check if our current dot next, we're going to, let's say this, let me say this. So check if current dot next value is in visited. So that's what we did, where when we move, we check if it's inside visited, then we remove. If it's not, then we add it to our new list, right? So check if it's in visited. Okay. and then we delete it and point its previous to its next in the case where it's invisited, okay? But in the case where it's not invisited, we add it to the visited, okay? And then at the end, we just return our new linked list. So basically the same thing I just did here is what we're going to write code for. So let's get to it. So the first thing we do is a base case. We check if the linked list ahead is fine. Then so let's do this. Nine. Okay. Next thing is to set the head. So I said, so I'm going to keep track now. Our current element will be the head, and then our visited, our tracker will be. So now to make it easier for it to make it easier for our tracker to keep only unique values, we're going to make it a set. Keep the value. So we know that sets will not have repeated values basically. So we'll set our tracker. We'll make our tracker to be a set basically. So now our while loop. So keep going. So while the next element is not known, we begin. So the first thing is our if statement. So we check if current at next of value is in our tracker. What we're going to do, if it's in our tracker, we change where it's pointing to. The current dot next now be current dot next. What I said, where instead of us pointing at it, instead of this is our current element, current dot next will now be current dot next dot next. So we're now pointing to the next one. So we're skipping 2 and jumping to 3 basically. That's what we're doing at this point here. Okay. And now our else statement. Let's have our else block here. Else, we add it to our tracker. In a case where it's not in our tracker, I'll add next value. Okay. And then when we add it to our tracker, we have to shift to the next one. And in order to shift to the next one, that's us basically setting the current one to now be a current next. So that's the shift now. Okay. And then finally, we have our return the linked list itself. So basically, this is a very quick and easy problem sort of showing how you move through a linked list. So I'll just run through it real quick one more time, and then if anybody like has a question or something, could just shoot. So the idea here is to remove. In fact, let's try to solve it with. Let's try to use our problem and go through. Try to use our problem to go through the solution we have. There's a double linked list. Put in both ways now. Okay. So we have our tracker. So now looking at this now, so we're taking in our double linked list, line 31. Okay, we're taking in this double linked list right now, and then first thing we do is to check if the head is none, we return none. But in this case, head is not none, obviously, because we have a head here. So we go ahead to set the current elements that we're on right now to be our head. So now we're at 2. Okay, so we set the tracker and we put in 2 in our tracker. So now what is happening here in our while loop? We said while the current.next is none, so current.next is none. So said while the current.next is not none, which means while we are not on the last element, because at this point current.next is this value here. Current.next the value is this value. While current.next exists, at this point we have current.next existing. So while it exists now, if current.next.value is in the tracker, so we should delete it, right? But in this case, as far as I'm moving right now, it's not in the tracker. So at this point, 2 is not in the tracker. So this is what's happening. So we add 2 to the tracker. So 2 is added to the tracker, and then we now shift it. We shift our current elements to now be current.next. So the next one now we're handling is 4. We check 4 is not in our tracker, right? So we do the same thing. We add 4 to our tracker, and then we shift. We're in 5. So 5 is not in our tracker. We add 5 to our tracker, and then we shift. Okay. Now current.next is now 2. Now we check 2 is in our tracker. So now if current.next.value is in the tracker, so set current.next to be equal to current.next.next. So we replace 2 with 3. So now we're at 3, and we check again. Okay, now we're at 3, we check again. So 3 is not in our tracker, right? So we add 3 to our tracker. And then if you check, it said, while current.next is not none. So as we add it to the tracker, this condition doesn't run again because the next one after 3 is none. And that creates our linked list, and then we just return the value. So like I think this problem is, as short as it is sufficient enough to sort of give us a wider understanding of how linked lists work, and specifically in this case, how a doubly linked list works. And that's basically it. Does anyone have anything they want to clarify or something?
Just the words current and next, are they reserved like keywords or?
So the add, let me open. I used the double linked list, but I just didn't bring it in. Where's it? I want to open a double linked list for you to see. So the add is, now if you want to, you know how you append?
I think it's a method for set.
Yeah. So you know how you append for your regular arrays? So you add for your set. Victor, correct me if I'm wrong.
Yeah, that's right. Yeah, you add to a set.
Yeah, so you add to the set. So same way you append for your arrays, you add to the set. Then what else did you ask again?
What, line 28?
Line 28?
Yeah.
You said line 20.
So
okay.
Line
so
28, the doubly
yes.
linked list.
Yeah,
I think
so
it should be capital, but I'm not sure.
Oh yeah, it's supposed to be, but this is me assuming I imported it. I've not imported it yet. Yeah, I just assumed it's been imported. So I just didn't want to
Makes
bring it in. I
sense.
wanted to solve, just wanted to solve without importing. basically. So this is assuming it's been imported, basically. Yeah. Okay. Any other questions?
I think Owen asks for the current and next if it's a keyword or something. I don't think you explained that.
Yeah.
Okay. Okay. So at this point is where I set the current, and then the next, I believe, is inside our double linked list. Just need to be sure.
So the
Sorry,
current is
it's
just a
been a
variable.
okay.
So current and next are really referring to something in this file here, the doubly linked list file.
Yes, basically.
Okay, right. And then usually the doubly linked list is kind of like near almost a template for most
It's almost like,
instances.
it's almost what?
It's almost like a template for most instances, no?
No, you'd have to, I'm not sure if Tom showed you guys how to, but you'd have to understand how to sort of build it out on your own first,
Right.
and then you'll be using it in most programs. Yes.
Okay.
Okay. So I guess that's basically it.
I just want to maybe say that on line 38, the set is converting an array with the current, but you could also use the set only with the first element being the current dot value. And yeah, but yeah, it's similar.
Okay. Okay.
Okay, I have a question. You remember when you were explaining, you said that there was a new linked list that you were supposed to, after the items are added on the tracker, then we were supposed to add them on the new linked list. The place where you were explaining, we had like two lists, the one for the set and also the one for the linked list. So I'm just wondering, in your code, where do you add it to the new linked list? Yeah.
Okay, so what is returned? So when I said the new linked list, what is returned is our like the final value, so like the new value, so like the result. So perhaps while I was explaining, I put it the wrong way. So sort of like the result instead of a new linked list. Yeah. So perhaps return our outputs would be a better way to put it. Okay. All right. So I guess that's.
Sorry, if you're.
Yeah.
Yeah, I was just going to say the return. You have the return inside your while loop, so it's like it should be like outside.
Out. Yeah. Out of. Sorry, that's my bad. You should return out of the loop. Else it's going to be infinite. Yeah.
So
maybe you should show the change version just so people don't get confused.
Okay. So the return was here. It should be here. Okay. Okay.
yeah, I was gonna ask. So any other questions for linked lists before we start with stacks and queues? All right. So I guess I'm gonna take over. So let me share my screen and get started. So I'm gonna go over mainly the concept of stacks and queues, and then also maybe some applications. Okay. So to start with, I'm just gonna I'm just gonna ask you guys to participate a bit. So do you know the difference? And I don't know, maybe is there anyone here that can explain what's the difference between a stack and a queue? Any takers?
I think with a stack, the last element that is appended to the array or the list is usually the first that is taken out. Just like when you have a pack of cards. So when you're adding cards, the one that you add last is likely the one that you pick from the top and you take out first. So the last element added is usually the first to go out. While for the queue, the first element that you add is usually the one that goes out first. Similar to when you are on the queue in the bank. So it's usually first come, first served basis. So the one that the element that goes into the array first is usually the one that you take out first. So that's just how I see it.
Yeah, exactly.
Probably to add on what Babatunde has said, I'd say, like, for example, when I talk about a queue, I see something that's horizontal, like a line, like you have said. And then when I talk about a stack, it's more vertical. So like when you are putting stack of plates together,
Yeah, I couldn't say it better myself. So that's exactly right. So the queue has a structure where the first thing you put in is also the first thing that comes out, right? So if I enqueue something like this 57, hopefully if I dequeue, it goes away. But maybe I switched it out. Let me see. Yeah, exactly. So yeah, so I enqueue something, right? This 50 here. So now this is the most recent thing in the queue. But the 65 came in first, right? It's on the head, right? So it has been added before. So it's technically our first thing that has priority. So it goes away, right? And with the stack, it's different, right? It's based on whatever thing I pushed right now should be the thing that goes away. Let me see if that happens, right? Yeah. So hopefully we have a good understanding of the concept. Any questions here? All right. So as you can also see from these examples, right? We're using linked lists to represent, right? And they're singly linked lists in this case, right? Could be doubly linked lists, doesn't really matter. But yeah, in this case, each node is one of these balls here on one of these circles, right? And the value is 22, and then we have the next, which is 58, right? So yeah, same thing with the stack. All right. So is there any preference which one you want to start first? I can go with either, right? So I'm just gonna go over simple implementation of each. And yeah, if there's any questions, just interrupt, all right? So to start with the queue, I think I'm gonna need a storage, right? So I need some place to save my data. And I'm gonna start with an array so then we can compare it later, okay? Versus the linked lists, I mean, okay? So yeah, I'm gonna start it with the storage and then I'm just gonna leave it at that, right? And then we have the enqueue, which is just a method that adds new data to the queue, right? And then, yeah, so the only thing we need to do is add it to the storage, right? In this method, because yeah, so let me comment here. This adds data to the queue. And the other method, which will be the dequeue, it just removes stuff from the queue, right? So it's not gonna need any arguments. Okay, so that's gonna be it. So with both of those both of these methods, right? We need to change something in the storage because that's where your whole queue is, right? That's where your data goes, right? So because we know that it's a first in, first out principle, right? I'm gonna add it to the beginning. It could be either one, but let's do that. So I'm gonna do insert and insert right at the beginning, index 0, and I'm gonna insert a new, I'm gonna probably rename this new value, okay? So that's pretty much it for the enqueue. And then for the dequeue, let's see. So we have to make sure that you follow the rules, right? Otherwise, it's not a queue, if that makes any sense, right? So to follow the rules, we need to remove from the end. So first in, first out, right? So it means that if I have some numbers, I'm just going to do the standard 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So if we have all of these things queued up, which one was queued up first? Any takers? So
9.
yes, exactly. Number 9 was queued up first because it's further along the queue, right? So it's at the front of the queue. In fact, it's the oldest element in the queue, okay? So every time we have a queue, the oldest element is the one that is going to be removed when we dequeue, right? So that's why we're removing from the end of this array, right? Okay. And so let me add this to the correct spot. So oldest element in the queue is removed. And in the case of the enqueue, well, we just we just add it to the beginning, right? So it becomes the newest element. So new value becomes newest element and is added at the beginning, or you could call it at the head if you're dealing with a linked list, right? Or index 0. Okay. So that's the base concept of a queue. There's really not much else to it. Is there any questions about how the queue works?
The 0 in line 11 is index 0.
That's right. So the way this is an array method, okay? So the way this works is you tell it which index you want to place this new value on. Okay. Same thing with the pop, by the way. The default value for the pop is the end of the array, but you can also specify where you want to pop from. Of course, here we don't want to change it, but we could also pop from a certain index if needed. Okay, but yeah, that's it. Any other questions? All right, so I'll move on to the stack then. Let's move on here. I think I'm just gonna, maybe not, I'll just type it out. So for the stack, it's a different principle, right? So it's very similar, but yet the different principle sometimes might be confusing. So we still need a storage to save our data, and I'm still going to use the array to start with, okay? but now we could call, obviously we can't call this in queue because this is a stack, it's not a queue, right? So we call it push, which technically it's the same thing it's doing, it's adding a new value to the storage, okay? And we're gonna do that later. And then we also have the pop, which is, let's say, the equivalent to the DQ, right? We're removing stuff from the stack. So in this case, we also need to handle something in the storage, right? So as you can see, it's pretty similar. Like the only thing I changed was the name of the methods and the class, okay? So let's see. We know that the last thing, sorry, let me let me type out the array again. 1 to 9. Okay, so now if we have this kind of stack, we know that a stack is technically the last in first out principle, right? So the last thing that came in is also the first thing that comes out of the stack, right? So what's if I called pop on this stack right here, what should happen? Any takers?
Number 9 will be deleted.
Sorry, number?
When you have the code, number 9 will be deleted when you call pop.
Exactly. Yeah. So the way the stack works is you remove and add both from the same spot, right? Because you know that everything you add is going to be the first thing to come out as well, right? So append is the method of arrays that adds stuff, right? So I'm going to append the new value if I'm trying to push, right? And if I'm trying to remove something from the end of the array, I'm just going to pop, right? I'm just going to return here as well, okay? So is there any confusion about this? Any questions? So let me see if I can do the same thing here. So oldest element in the queue. No. So in the case of the stack, it's the most recent element added is removed. Okay. So it's the other way around. Where in the queue, when you remove stuff, you remove the oldest thing there. If you remove on a stack, it's the most recent thing. Okay. So and that's pretty much it. Is there any other questions? All right. Well, what do you guys want to do now? Do you want to do some sort of code challenge or anything else specific to this? Any suggestions? What would help you understand this better? Anyone? Otherwise, I'm just gonna do like a basic code challenge. I don't know if that is something that you want to see.
Can you go through a basic code challenge using Q and
Sure.
stack and then explain it also?
All right, let's see. So I do have, let's see. I do have some things here with stacks. So let's take a look. So I think I'm gonna go with this one. So I'm taking this from HackerRank. I'm sure there's many of them. If I just write stack, that might happen Yeah, might see a bunch of exercises here, right? This one might be familiar. Did anyone ever did this one with the brackets?
I did.
Sorry, who? Ifyok. Yeah. Of course, of course. So yeah, this one with the brackets, it's really interesting. So what they're asking us to do, right, is we get a string to a function, and we have to return yes or no based on if we have matching brackets for all of them or not. Okay. So for example, this line here, which I don't know if you can see very well, this line here has an opening bracket for well, this brace here, right? And then a closing square bracket, which technically makes this invalid, right? Because you can't just close something in the middle of the other one, right? So it, does everyone understand what the problem is trying to do? For example, this one is valid because we have the correct brackets on the correct place, opening and closing brackets. All good? Everyone good with the problem? All right. So yeah, let's just code it out. So let me see. Yeah, okay. Mm-hmm. Okay, we have an expression here, and then we'll call something. Okay, so I'm gonna start out by creating a function. Okay, I'm gonna give it the same name as the problem here in the Yakarang. And yeah, it's just gonna receive some a bunch of brackets. Okay, but I'm gonna call it yeah. Check. Call it like this.
I have a question. I thought that Nini HackerRank they usually give you a place where with like Nini where they define the function. Like when you scroll down or something, or it doesn't usually happen.
Sorry, can you repeat? I didn't understand the question.
When you're solving like a challenge in HackerRank,
yeah,
they usually have some place where you're supposed to answer it. I usually think that's the case, but I'm not sure. I wanted to know.
Yeah, this is it. So this little code terminal here is the place. We could do it in any language actually. It doesn't have to be Python. And
no, you don't. I don't think you understand what I'm trying to say. When you scroll down, you see here where it's numbered, 18, blah blah blah. So
yep.
There's usually some place where they usually like write for you the function. Like you see here in line 9 where you have this function. They usually have it already. I'm just wondering.
I get it.
I think I've done one or two challenges. So I'm just wondering why do we have like to start from, you've understood?
Yeah, so
like from scratch.
I do know that might happen. In this case here, I can see that it's fetching input right from the challenges that will run when I submit the code, and it's going through all of them and getting each one of them in a string, right? So what I'm gonna do is just run my function here with the expression right as a string. So it will just print out the needed stuff, which is just yes, no, yes, right? So that should work for us. So I can also print. No, I probably
that's okay.
can't,
That's
but,
okay.
But yeah, I'm sure. Yeah, if it doesn't work, we'll see. We'll take a look at that. But yeah, I think it will. So. So again, like I was saying, right, we just declare the function and we get our brackets to check, right? So now here's the strategy I'm thinking, right? We know that for this opening bracket, we need the other one to close it. And for this specific one, we have this one, right? So there's a specific character that it needs to match, right? So my first thought is a dictionary with key value pairs, right? So the way brackets work is going to be, I'm going to have some kind of closing bracket that matches to an opening bracket, okay? And that's going to happen for all of them. So I'm just going to type that out like this and like this, right? And this works because the character is different to open and close, okay? And we'll talk about that later, and what we would do if the character is the same. But yeah, so that's the first thing we can think of, right? That's what the problem gives us as well. We have that data, so that's the first thing to do, and this will help us. This will help us a lot, right? Next thing I'm thinking of is we have this string here, right? But we kind of need to check each bracket one by one, right? So to do that, it's a for loop, right? We just for loop over each character in the string, right? So let me do this. I'm actually going to call it, maybe there's too many things called brackets. I don't know, but I would call it brackets. Okay, so for each bracket in our string, okay? And we're gonna go over all of them. So we want to check all of them to see if they have the correct order and the correct opening and closing, right? So, but how are we gonna do that, right? What data structure do you think between stacks and queues would help us with this kind of problem? We need to keep track of which bracket opened at which time, so we know that it needs to close at a specific time afterwards, right? So how do you think we could keep track of it between stacks and queues? 50% chance of guessing it right if you don't know.
I'm guessing Q.
Are you sure? So what happens with the queue? Let's take a look. So for example, the first thing in is the first thing out in a queue. Well, maybe it could be possible. Actually, the solution I had in mind was with the stack, but it might be possible. What do you think, Victor and Ifyok? Is it possible? I think it could be. So first thing in is also the first thing out. Yeah, it could be. So let's try with a queue, okay? I didn't prepare for this, so let's see.
No, let's do it with stack. Let's just do it with stack.
But let's take a look, right? We start with a queue, and the only rules with this array here is that we insert to the beginning, right, and pop from the end. Okay, so that's going to be easy to do. Okay, so how do we know, what's the difference, right? How do we know which one is the opening and the closing one, right? And that's actually why I chose to do the closing one as the key and the opening one as the value, okay? Because now I can check, I can see if my brackets is in my dictionary, okay, then it is a closing bracket, right? Does that make sense? So if my character right now is in the dictionary, so in these keys, it is a closing bracket, okay? So with that in mind, we can continue and say, so if we're closing, what needs to happen, right? If we're closing, we need to have something opening for that closure. Otherwise, we have an invalid string, right? So let's see. Check if we have an opening brackets that matches this closing brackets, right? And else, so if it's not a closing bracket, so let's say if it is and here is basically if it is not a, well, if it is an opening, right? Okay, so if it is an opening bracket, okay, so we go into the else, right? What we're going to do is place it in the queue, right? That's the most logical way to store the data here, right? Let me see if that's going to work. So queue dot insert 0, and we're going to insert the bracket itself. Okay, so is everyone clear so far? All right, so as you can see with the queue, right, the way we add stuff is with the insert, right? So that's what I'm doing here, okay? And the way we're going to remove stuff is going to be with pop, okay? So why do I need to remove stuff? Because I need to remove stuff because I need to check where's my opening bracket to this one that's closing, right? So here it's where the magic happens, let's say, because here I'm going to check like if the thing that comes out of the queue, so my opening brackets, okay, is queue.pop. Okay, so if my opening brackets is different than the one I have it right here, right? I know which one it is, so I just need to check if it is different. So if it's different, so of brackets at the specific brackets, okay? Too many brackets. I might rename this to make it clearer, but yeah, we'll see. And of course, you don't need this. This is Python, okay? Okay, so now what happens? Like our opening bracket does not match with the one we have in the dictionary. So what happens is we have an invalid string, it's invalid, like the brackets are in the wrong place, right? So we're gonna print no, and we're just gonna break out of the loop because we don't need to process anything else, right? It's done, it's invalid, right? So we stop. But I do want to check if this is going to work. So let me see. So what happens? Well, else, right? If it matches, right? If the opening brackets match, then we have a good one. So we continue. Yeah. Okay. 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 So. So what do we return? I guess it's not much about return, it's more about printing in this case. Okay, so what else do you need to check at the end, right? Any ideas on what's missing here? From my side, I can see that we're looping the string, right? We're checking if our brackets match with each other. And if they don't, we print no, right? But is there anything else that we need to do to check before we print yes, it is a valid string? What consists of a valid string in this case, in this challenge? So what I'm talking about is the queue itself, right? Our queue might still have some brackets that we didn't attend to, that were opened and not closed, right? So it means that our closing brackets never went in here, like we didn't have closing brackets to go here and check, right? So in that case, if we still have something at the end of this loop in the queue, right? It means that something was left open. So it's still an invalid string, right? So in this case, I'm going to check, if the length of the queue is more than 0. In that case, print no, because there's some brackets there that were not closed. Else, I'm going to print yes, which I don't need the else. I can just go like this. Yeah, I do, sorry. I do need the else. Okay, like this, right? So I don't know if this is gonna work with the queue, to be honest. I'm just gonna test it out. But if it doesn't, I'll check it with the stack. Yeah, it doesn't, okay. So it's printing no, 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 no. So it might be because of the...
Yeah, I think a queue should work, right? I think it's just the extra balance.
Yeah, this part here, right? It's just this part here that is messing it up. So let me print
No, just leave it. Just leave nothing.
Like this? Yeah, but
Yeah,
it's printing correctly.
Yeah, what I mean is don't print anything. Just leave it as it was, like by default. So you have just line 39, and that's where it ends.
Yeah, but in that case, it doesn't run the function, right?
Yeah, it still does.
Really?
I think so.
Yeah, I don't think it did. So I think it's my code. I don't think this is it. Let me just go like this and check. So in this case, if it breaks, so first thing I'm gonna do is try it with the stack, and then I'm gonna try it with the queue, just to make sure it's not this, okay? So I'm gonna change everything into a stack. I'm gonna append to the end and remove from the end instead of beginning and end, okay? Let's see if this will work. Okay, so if it is equal to 0, we print yes, like this. Yeah. Well, why is it taking so long? That's not good. All right, let's see. So we have yes, no, no, yes. So yeah, it is printing no twice. That's what I was concerned about, because what's happening here is we have it here printing no, right? And it breaks out of the for loop, but it also checks here, and it's still no, and it prints it again. So let's see. I think I'm gonna do it differently. So if I do this is valid and place it as a Boolean value, it's technically gonna be a no up until it is a yes.
Yeah. How about you just return after you print no, so you don't have to
Of course, makes much more sense. Of course. So yeah, return, of course. So yeah, exactly. That makes much more sense. Let's see if that works. Exactly. Yeah. Yeah, return makes much more sense. What I was gonna do is use a boolean instead of printing right here. I would do it in the if statement. But yeah, it still works like this because now the return is gonna completely move out of the function, so the function completely stops instead of continuing down here. Okay. So yeah, that's our solution with the stack. Now, if I want to change it into a queue, somehow it made sense to me at the beginning, but I need to think how I would do that, right? But let's just, for now, is there any questions about how this works? Yeah, just overall questions or feedback you guys have.
Can you repeat from line 18 to line 23?
23. All right.
What are you doing there exactly?
Yeah. So we're looping through the string. We have each bracket one by one. And then this if statement checks if this bracket right here is in our dictionary. So when we do this right, what we're actually doing is checking if this is a key of this, right? And yeah, when talking about dictionaries, right? So this is a key of this. So what I'm actually doing is checking if it is a closing bracket, because I chose to write my dictionary where my closing brackets are the key values, are the keys of my dictionary, right? And the values are the opening brackets. Okay, so that's my personal choice because it kind of helps me know, differentiate which one is the closing, which one is the opening bracket. So in this case, I wrote them as keys and I check for it here. So if it is a closing bracket, we're gonna check if we have a matching opening bracket that appeared before it, right? That's why we have our stack, because other brackets that we've moved through before in this string here have already been appended to the stack eventually, right? So what we're gonna do is check, we remove something from our stack, remove one of the brackets, so we have our opening bracket that should technically match, right? But if it doesn't in this if statement, right? If it doesn't match, then it's invalid. So we stop the function and print no, it's not valid. Okay, so that's what we're doing here. And yeah, our stack makes it so that the brackets are correctly placed in the order that they're being opened. And that's why with the queue it didn't work. So with the queue I would have to change the whole, probably the whole algorithm. I'm not sure how to do it with the queue, right? But I'd have to think a bit more about it. Okay.
Thank you.
Yeah.
Okay, can you like just go down there where you are passing in the balance brackets function?
Yes.
Okay, so it's okay. Just wanted to see how you passed it. It's okay.
Yeah. Let me submit to see if it passes everything. I think it does. Okay, it doesn't. Let me check. It might be runtimer. That's a bit strange. Oh, I see. So I think, well, I'm not gonna give it away right away. So I'm gonna ask you, do you guys have any idea why it says runtime error? Just gonna give you guys a minute to analyze. Any ideas? No ideas. All right. So the reason it says runtime error is what do you think would happen if we try to pop from an empty stack? Right? It will give you an error. So the problem here is we need to check if our opening bracket is different than the opening bracket, right? But we also need to check if the length of the stack is more than 0. So length of stack is 0 or stack.pop. Okay, so if our stack is empty or the opening bracket does not match with the other one, we print a no, because we found this closing bracket here and either the stack was empty, meaning that no bracket was opened, there's not even one open bracket in our stack, so it's impossible we have it, so it's invalid. Okay, or it means that our bracket that we got from the stack does not match the other one we have here on the dictionary. So there's two conditions here which we need to check instead of just one. So that might fix it, and it does. Yeah, so that was it. Questions about that? Let me just scroll up here. So yeah, okay. All right, all good? Everyone is good with this? Okay, so I'm gonna move on then. Moving on, going into the queues again. So the only thing I'm gonna do now is show you the difference between using an array and a linked list in queues and stacks, okay? So I'm gonna import it. So from my W linked list, this is pretty standard. This is what you have from your projects, okay? So from, import the W linked list class, and I'm gonna use it here. Technically, it doesn't, yeah, technically it doesn't matter if it is a singly linked list or a doubly linked list. It's just the way it works might be a bit different when you're trying to add to the head or remove from the head, things like that, in terms of runtime. But I'm going to use a doubly linked list. It's still possible to do it with the other one. Okay. So what do I need to change now, right? Well, let me just do it like this. I'm gonna comment this. That might be the smartest option here. So we have something to compare to. And then copy paste like this, okay? And now we're gonna check exactly what we have to change. So here we initialize the doubly linked list. So we create a new doubly linked list, say here, okay? So that's our new storage instead of the old array. Then we need to change this because our double linked list does not have an insert method, right? Our storage has changed, so we need to change everything else after it. So now we need to add something to the beginning of the list, right? And that's just going to be the head, right? And we're going to add the new value to the head. Okay. So that's the switch. Let me go ahead and make a comparison here. And then lastly, the DQ, right? The DQ just removes from the end of our list, right? So technically we just remove from tail, which is the end of our list, right? So that's how easy it is to change from an array into a linked list, right? It's just about the methods you use, okay? And that's our queue. This already, it works the same, exactly the same way in terms of a concept, but in terms of the runtime, it's different, right? So if we analyze the add to head and the remove to tail, okay. So you can see that add to head is pretty much constant time, you could call it, okay, because we have just simple operations. We are assigning a variable, increasing a number here to the length, right? Just assigning new values to the head and tail, or just creating the next connection into the new node. Okay, so basically all simple operations, okay? No, like, yeah, there's no for loops, there's no do I make myself clear? I don't know if it is understandable. Add to add is technically O of 1. That's what I want to say in general. Okay. Any question about this? All right. So the other method is remove from tail. Let's take a look. Go back to the doubly linked list. Remove from tail. There we go. Remove from tail. Let's get some participation. So which one it is? O of 1, O of n? Which one? O of n squared? What do you think?
O of 1.
Yeah. So we're calling this just assignment, right? We're saving this value, our tail value, and then we're deleting the node itself and returning to that value, right? This delete, by the way, is just a method like in the node itself, I think. Let me just check. Yeah, so yeah, it just reconnects the previous and the next pointers. Okay, it's not doing too much. So yeah, exactly. So it's O of 1. So is that clear to everyone? The constant time here?
Yes, if it was ON, what kind of changes we would have?
Well, it's not, right? That's the point. The thing is that with an array, it is O of n, right? That's what I was gonna talk about next, right? We have this insert here, and think about how this works, right? Think about how the insert will work. In a normal array, let's say I'm just going to use 1, 2, 3, 4, 5 again. Okay, so in a normal array, we have this. Imagine this is in our storage right now, and our storage is an array. but we want to insert right at the beginning, right here, right? The thing is that in memory, we have, I don't know, some address, right, with the number 1, and then some address with the number 2, etc. Right? For each value, there's some kind of place in memory for that number, and we want to add it something before the number itself, like like it's impossible, right? It might be empty, but it also might be filled out in memory, right? Usually it is occupied. Okay, so what your computer has to do is the same thing, like relocating everything to a new spot and adding the new number here in this place before adding all the other ones. What does this mean? It means that it takes n, right? N, which is our input, right? The length of this array is n, right? Which is technically an O of n operation to relocate the whole array. Is that clear?
Yes.
So basically, this insert method is much more expensive than the add to head, which is just O of 1, right? And let's see, we did have the pop. Sorry, here it's pop. We did have the pop, but I believe that the pop is still O of 1 unless you specify an index, right? Because the pop it removed from the end, so technically it doesn't do much. If that's clear, but if we specified something to delete specifically, it would still have to loop up until there. Yeah, correct me if I'm wrong, if you're Victor, but yeah, I think that's how it works for the pop. But yeah, the most important thing is they insert the difference here, right? And it's quite a big difference, right? Like if you look at the graph, if I go here into the big O notation website, let's call it, if you look at the graph, like if you have a O of n, it's much more operations than just O of 1. It's a straight line like this, right? It's just to be clear, like it's a O of n is still a fair, like it's an average type of runtime. It's fine, right? It's not like it's gonna break. But if you have a lot of instances in an application where you have O of n, but you could have O of 1, that makes a lot of difference over time, right? So that's the goal here. Yeah, just improving performance with the linked lists. And yeah, Victor already discussed how bad the other ones are after O of n. Okay, so yeah, so yeah, that's pretty much the big difference. Any questions about this change between the arrays and linked lists? All right. Yeah. So you guys are gonna help me with the stack then to finish this off. That's the last topic I have here. Since you guys, everyone has understood how it works, let's see. So how do we change this? Anyone can step in. No takers.
Okay, let me go.
All right. So what do you think here to get started?
Okay, I think the double linked list should replace the array.
Okay.
Okay. So instead of having the append, um, you have add to tail.
Okay.
Then instead of having the pop, we have remove from tail.
Anything else?
Nope. I think that's it.
Does everyone agree? All right. I hope silence means yes. So yeah, that is exactly right. So you on a stack, you add to the tail and remove from the tail. Just to be clear, technically it doesn't matter, right? You can do add to head and remove from head. Okay, it's the same thing as long as you do the operations on the same side of the list. Okay, it doesn't matter because technically it's doing the same. It is the same concept and the same order of the elements inside the stack, right? So yeah, and same thing with the queue here. You could change add to head into add to tail, but you'd also have to change this tail here into head, right? So they are how do you say it, interchangeable. I don't know if that's a word, but yeah, you can switch, right? It doesn't have to be head and tail. You don't have to like know it uh, in your head. Like it can be either one, as long as you know that a stack does it on the same side and the queue does it on opposite sides. Okay. All right, that's pretty much everything I had to talk about. If there's any questions, now's the time. And yeah, we're pretty much reaching the end of our after hours.
No, I
Any?
don't have it. No, no. Are you going to how say put this recorded video in the Slack?
Yeah, of course. So usually I need to upload it to YouTube because of the file size first. So it might take maybe not today, but might be tomorrow because it takes a while to upload and all of that. So yeah.
Whatever, it will help us later on. That's why I'm asking also.
Yeah. No problem.
Okay, I have a question.
Yeah.
Yeah. Okay. So so instead of do they have different run times? Like instead of having the pop, when we have the pop, does it like run faster than having the
let me
remove from blah, blah, blah?
confirm. Let me confirm. I do believe that pop doesn't make as much of a difference as inserting and pushing. Okay. But
Do you mean popping from an array?
sorry.
Do you mean popping from an array?
Yeah. So it is O of 1 to pop the last element in the array, right? But it is O of n to pop an arbitrary element. That's what I said before, right? So when we're doing pop like this, the default is it pops right from the end of that array, right? So it's O of 1 because literally what it does is remove one element that he already knows where it is. It's really simple. If you take an array, you know where is the last element of that array if you do this, right? So this is O of 1, like easy to delete something like this, right? But if you imagine you switch this, right? If you switch this into tail and head, okay? This is the queue, by the way, okay? So if you switch this, now you're removing from the head. So technically you have to pop the first one. So this is O of n, because if it is a specific element that you need to remove, it's O of n. Okay, so hopefully that made sense. But yeah, there's a lot of information on how POP works here. But again, the most difference comes in when adding stuff, not removing them. Okay. Hope that was clear. Any other questions?
No, I'm okay.
This is awesome. Thanks, guys.
Sorry?
This was awesome. Thanks, guys.
Oh, yeah. Thank you.
Yes,
Thank you.
it was a perfect class. Thank you very much, all of you, all of three of you.
Yeah, yeah, thank you as well. So I think we should call it a day here. We're pretty much all tired. So
Yeah.
let me just stop sharing my screen, and I'll see you guys tomorrow, I guess.
Yes. Take care. Don't forget the video.
Of course not.
Tomorrow.
Yeah, see you.
Thank you very much. See you.